you're given a series of points to plot. Everybody seemed to plot those points very quickly and efficiently, and I think with good accuracy. I've plotted the points here. I'm not going to read the coordinates of the points to you. You have them, and as I say, everybody was able to get a pretty good plot. Then the instruction was, first the instruction was that your graph should go at least from x equals -3 to x equals 12, even though the points don't go that far. But then also that the y-axis go from about -5 to 15. Okay, now when I look at this, I wonder just how well I plotted those points. In any case, we're going to take my plot. Okay, here's my plot, and then the instruction was to plot a straight line that comes as close as possible on the average to the points. Now, here's the line I sketched. Hopefully you can see where the points are. I can make the line a little higher or a little lower and get closer to some points and further from some. Where does it best fit the points in the sense of coming as close as possible on the average? I can also change the tilt just a little bit. So by raising or lowering the point and by manipulating the tilt, I can get closer or further from my goal, which is to get the minimum average distance between the line and the points. Now, I think I did fairly well here, and of course that's just a freehand attempt, and no reason to expect it would come out really well, but kind of went where it was supposed to. We see we've got 4 points above, 3 points below. The points above are a little closer on the average than the points below. So it looks like I came pretty close to getting a decent line, but I think I could have lowered it a little bit. I think these points are a little too far from the line. I think if I lowered it a little bit or maybe changed the angle a little bit, I could do somewhat better. And there's also the fact, technical fact, that we don't need to think about too much if we're doing an eyeball estimate, that really we're trying to minimize the squares of the distances from between the line and the points, and it's the vertical distances, not the distances perpendicular to the line. We don't worry about that. Just try to get as close as you can on the average to the points, and you should be relatively close. And then there are calculator and computer applications on almost every calculator and computer that allow you to determine really the very best line that can be fit to those points in the strictest sense. And that would be the line that we would use in what we call a regression analysis. Now, really, right now, though, I want you to do this by hand. I don't want you to bypass the idea of what's going on here, which you will do if you just rely on the technology. So I don't even like using the technology in this course. I won't even ask you a problem on a test that requires you to use that technology. If you understand what's going on here, then it's very easy to learn how to use the technology and learn how to get a really good result. Okay, so the process here. Make the best line you can that comes as close as possible on the average to all the points. And then choose the point on the line where x equals -3. That would be this point here. And the point where x equals 12. That would be this point here. Estimate the y coordinates. Okay, well, 12 looks like this comes over pretty close to 15. So I'm going to say 12, 15. Over here, it looks like this projects pretty much over to -3. So I'm going to say this point is -3, -3. Now, notice two things. The line didn't even hit any of these points. The best line will generally not hit any of your data points, and there's no justification for trying to make it go through any of your data points. A lot of people, if you give them this problem, will draw a line through the first and the last data points. That would be a disaster here. The line wouldn't have enough slope. You'd have 1, 2, 3 points above, only 2 points below. And you would not even come close to minimizing the average distance between the line and the points. Okay, that's not something you ever want to do. You want to come as close as possible to the average, and that's the way you want to look at it. And if you went through the first and last points on a test, I wouldn't, you wouldn't lose the whole problem, but I would penalize that. Don't want to see that. We take 2 points that aren't data points, 2 points on the line, and it's usually best to use 2 points outside of the range of your data. Okay, so I take those 2 points, and then I just get the equation of the straight line through those points. That's very easy, despite the fact that I did it wrong about 6 times in a row while everybody was working on it. I just looked at something wrong and wrote the slope down incorrectly. And then I made a series of mistakes. That wasn't one of my better moments. Okay, anyhow, my line goes through -3, 3, and 15, 12, 15. So it's really straightforward to find the slope of the line and then to find the equation of the line. Okay, the slope, well, the rise from -3 to 15 is 18. The run from -3 to 12 is 15, so the slope is rise over run. 18 over 15 reduces to 6/5, and if you want the decimal approximation, which I'm not going to use in the solution, it's 1.2. Okay, and also, if you do this in the manner that we've done it, the slope is y minus 15 over x minus 12. Remember, we take a point out here and call it xy. We sketch the basic triangle between that and the closest point, or the other point, it wouldn't matter, and set the slopes equal. So the slope between 12, 15 and xy is y minus 15 over x minus 2. So if that slope is 6/5, then xy is on the line. That's a bit of logic that I encourage you to understand. Not required, kind of a little extra thing. It just makes you smarter, marginally smarter, to understand that. Okay, so we set these equal, and that's exactly the same as using the 2-point form or the point slope form of the equation of a straight line, which is, would be y minus 15 equals 6/5 times x minus 12. Y minus y1 equals m times x minus x1. I prefer to go back to the geometry. You'll be better and smarter if you do. Instead of just quoting this formula, you'll understand what it means and where it comes from, and you'll understand the logic of what it means for a point to be on a graph. Okay, regardless, either way, whether you do this or this, well, this is just a rearrangement of this. We just multiply through by x minus 12. So whichever we use, we're going to get y equals 6/5 x, and 6/5 x, minus 6/5 of 12. 6 times 12 is 72. You shouldn't need a calculator to do that. 72 over 5. So we have negative 72 over 5 from 6/5 times negative 12 plus 15. Well, 15 is 75/5. So we have negative 72/5 and 75/5, which gives us 3/5. So our equation is y equals 6/5 x plus 3/5. Now there's more to the problem, but we'll look at it in a minute. We're asking how far is the line above or below the point 5, 6, which is one of our data points.